I don't want most people to miss a class, you know?
Mhm.
So, okay. So let's go ahead and get this homework up. So, all right. So the homework. Did you have problems on any ones in particular or just in general?
In general.
Okay. So the general idea of moments is it's basically a force applied at a distance. And I'm going to go ahead and just open Paint so we can kind of go through this. So like the first problem, basically you have like a lug or like a bolt or something that you're trying to unscrew, right? It's a beautiful, yep, very good. Okay, so basically, the idea of moments is it's rotation. Torque is kind of like the rotational equivalent of force, but it is created by a force. So basically, when we're looking at torque, we're looking at some sort of force that is applied at some sort of distance, and we always want to be looking at the perpendicular force to that distance. So we have a distance d, we have a force F, and then what we're looking for is the words moment and torque are basically the same thing. So we're looking for the moment around this point here. So this would be the moment that we're looking for. And the way you find it is basically it's just the perpendicular force times that distance. And that is basically all you need to know for moments. When we start doing equations of equilibrium, like we did with forces, it's basically the exact same thing. So you know how when we did sum of forces x equals, let's say like an applied force minus a friction force?
Yeah.
Moments work basically the same way in that you're just adding everything up. So like when you're doing like a F net for force, you do force plus a force plus a force, so on with all your forces, right? That are in the x direction. With moments,
Yeah.
basically the same thing. You do your sum of moments. So sum of moments in the z axis is just going to equal moment 1 plus moment 2 plus moment 3, so on and so forth. Okay? And when we're doing statics, these are always equal to 0. So if I had something where I had, let's just say we have a bar, just some random bar, and it's got a little swivel right here, and it already has a moment, moment 1 here, and we'll say that's, I don't know, 10 Newton meters. Oops, a little messy. Newton meters. But there's also a force being applied at the end of the bar. Okay. If this force is equal to, let's say, F equals 5, and we'll say that the distance of this bar is equal to 10. Basically what we do for sum of moments, and did you watch the recap class?
Yes, I did.
Okay. So keep in mind, standardly, counterclockwise, it's positive. Clockwise, it's negative. Okay?
Yeah.
So basically what we do here is we have a moment already, so let's go ahead and add that. And it's going clockwise, so it's negative. So minus 10. And then we have a moment that's created by this distance and force here, right? So we're going to say, which way is it going to spin? It's going to spin this way, right? Which is counterclockwise. So we'd say plus 5 times 10, because that is the force and the distance, and they are perpendicular to each other. So when we finished our moment equation, basically we'd say, well, this is not going to equal out. There should be something else here, but our net moment would be 40, because this equals 50. This equal, minus 10 goes down to 40, right? So this would actually not be a static system because it's moving, but yeah. So basically moments work the same way as our forces did, right? The only difference is that you're multiplying a force by a distance to get the moment, okay?
Rather than
What now?
adding.
Yeah, rather than adding. I mean, you add all of the different moments together, but you multiply the force by the distance to get the moment, right? So basically, moment equals force times distance, and then the sum of the moments equals all of the moments added together. Similarly to, there's a force here, you have a force, and the sum of all the forces in the x direction is all of the forces in the x direction added together. So in that regard, it's the same that like what we've been doing. For the homework in particular, let's go look at that. Let's see, homework. So the first one, we have that there's a guy tightening some sort of, like a lug, and he's applying a torque, which torque and moment are basically the same thing, of 110 Newton meters. It's at an angle of 90, which means it's perpendicular. The moment arm is the distance. So what force is applied if the wrench is 0.4 meters long? So basically, it's actually nearly the exact same as what we did here. And can
I think I have an idea of how we would do this.
Okay. You want to
Can you go back to the homework?
Yeah.
So if the moment or torque is 110, then it would be the force perpendicular times d equals 110, right? And then in that case, you would go the wrench, and then it would be force perpendicular times 0.4 equals equals that, and then would you put 90 degrees in for the force perpendicular to it?
So you don't really, the 90 degrees is if, because it's at 90 degrees, we're at it is perpendicular. 90 degrees means perpendicular, or vice versa. So basically what it's saying is, here's our wrench lug thing. There is a torque about it, let's say this way, which is 110. And there's some force being applied over here. It is at a 90-degree angle, which means it's perpendicular. And it has told us now that the distance is 0.4. So yes, what we'd do is we'd say our torque is 110, which will equal our force times our distance, which is 0.4. And then basically we're just going to divide both sides by 0.4, which equals some number. It is 110 divided by 0.4.
275.
Yep. So equals F, right? And that is our answer there.
And would it be Newton meters?
So force is in newtons. So force is newtons. Distance is in meters. So torque, which is here, because it's force times distance, it is, so torque is usually kind of like that symbol. Torque is in Newton meters because it's newtons times meters, right? So
Right.
force is newtons, distance is meters, and torque is newton meters. Okay, so the second problem is a little harder, but it's or a little, I guess, different. This is more of the conceptual bit of how do moments work where you're applying them. So basically, constant force F is applied at different points. So B, C, A, D. And we want to basically rank how large the torque is going to be exerted by these forces, okay? And this is assuming that this is drawn to scale. So we want to know the moment around this point here. So one of the things about torques and moment is if there's a force that is passing through the pivot point, as B is, then it does not apply a moment, because it's not going to rotate that. It's just pushing through it, right? So
Right.
B is 0. Okay. The force may be something, the force could be huge, but the torque applied by B, so actually I should write that as torque from B equals 0, okay? And the reason why is the distance is 0. So like if B equals 10, right? The distance between B and here, because it's passing straight through it, is 0, so it'd be 10 times 0, which equals 0, right?
Mm-hmm.
So the torque that B causes is 0. And then from there on, we can basically say which one of these is going to cause the largest forces. Well, we can see that from the pivot out to D is larger than the pivot out from C, perpendicular to the force, right? So this is perpendicular, and this is perpendicular. So because this has a shorter distance than this one, C is going to be less than D, okay? We can also say, similarly, that A is further out than C, so A is also probably going to be greater than C, okay? This is all just because the distances are larger, right? So distance A is greater than distance C. Okay. And because it's greater, that's why the torque is going to be greater. Since torque is force times distance, if the distance is bigger and the force is the same, then the torque is going to be larger, right?
Okay.
So if distance gets bigger, torque will also get bigger. Now, when we look at D and A, D and A are this, if this is drawn to scale, are the same distance away, okay? But if you look, D is at a perfect right angle to its to the moment arm, which is this line here, the distance, and A is not at a perfect right angle. It is at it's tilted, right? And it's saying that these are all the same. Yeah, so A is at an angle. So it's saying all of these are the same force, which is F, right? And we know that if F is tilted, the component of F, which is actually perpendicular, which is going to be the Y component, is going to be smaller than F itself, because we would be doing like, if there's an angle theta, right, it would be like F cosine theta, which is going to be less than F. So because of that, we can say that A is less than D. And then if we just put all these together, right, then we say, well, B is 0, so it's the littlest. C is closer, so it's smaller than the other two. A is less than D, so that is our ordering. Okay?
Oh, it goes, so the greatest is, no, so the greatest is D, then A, then C, then B.
So this side is small, this side is big. Do you know what this symbol here means?
Greater than, less than, greater
Yes.
than, less than, those signs.
So the thing on the smaller end, or on the pinched end over here, is the thing that's smaller, and the thing that's on the big end is bigger. So yes.
Okay.
So this would be our ordering, and this is kind of to show you how some moment rules work. Basically, it's if distance is bigger, the moment or torque will get bigger. If force is bigger, the moment or torque will get bigger. If either of these things get smaller, the torque will get smaller. Okay? Does that kind of make sense?
So, yeah, so if distance gets bigger, torque is, so if any of those gets bigger or smaller, torque gets bigger or smaller.
Yes. And usually you would put math into this so that you would know exactly whether or not C is bigger than A or A is bigger than C. But because it's saying all the forces are the same, and this distance is significantly greater, we're just going to say that it is, okay? If A were coming at an angle like this, that might be a different story. But because it's so much further out and it's not at a very harsh angle, we can pretty safely say that it's going to be bigger than C. Because there's kind of a give and take between force and distance in this equation, you know. So basically, number 2 is just to try to show some of those little moment rules. Number 3 is more like the first problem where we're just solving. So draw. So we have this 15 kilogram box sitting on basically a seesaw. And it says that it is at a distance of 5 meters from the place that it rotates, okay? So what that means is from here out to the middle of the box is 5 meters, okay? Now it asks,
Okay.
what distance must another 10 kilogram box be to keep this thing from not rotating? So basically it's saying if I put a different box over here that was 10 kilograms, right? What distance d does it need to be, right? And what that means is what we're trying to do is we're trying to set moments equal to 0. So what we need to do is determine the moments being caused by these boxes, okay? So what force is going to be, is the box going to be applying? It has a mass, right?
Right. I'm trying to wrap my head around this.
So right now, let's just look at the forces. If we have something that is 15 kilograms, right? And it's just sitting on a table, what forces are acting on it? I can draw this better. So just the forces, okay, of the box. If it's sitting on a table, just normal sitting on a table, what forces are on the box?
Gravity?
You there, Carson? Oops, sounds like he's having some audio issues.
Oh, yeah. Can you hear me now?
Yep.
Oh, so it would be normal and weight.
Yes. So we would have the weight force going down, and we'd have the normal force acting against it. But the thing is here, we're not really looking at the box itself. We're actually just looking at this seesaw. And so what that means is the box is pushing against the seesaw with its weight force, right? So
the normal force and the weight are both negative.
Well, so the normal force we don't need to worry about because we're not actually looking at the box itself, right? The normal force is a force being applied on the box by the seesaw. But if we're just looking at the seesaw, we can see that there is a force being applied on it by the box, which is the box's weight, right? So basically,
Okay,
if you put something on something, or if you put an item on like a seesaw, it pushes the seesaw down because it's heavy, right? So each box is going to apply a weight force, and we're just going to call them weight 1 and weight 2, okay? And yes, they're both going to be pushing down. So if we have something that is heavy, something that's applying a force, and it's 5 meters away, can you tell me what the moment caused by this box is on this pivot point? So we have our force here, we have our distance here, right?
Right. So first, we need to turn the 15 kilograms to define the weight.
Mhm.
So we would have to go mass equals weight times gravity, right? Weight times 9.8.
Weight equals mass times gravity, yeah.
Yeah, that's what I mean. It would be 15 times 9.8.
Mhm.
Put on enter. So that's 147. That's what I
Yep.
got.
Yeah, it is. Good. So weight 1 is 147. What is weight 2? So we know it's 10 kilograms, right?
98.
Yep.
Sorry, 9 point. Oh,
No, 98, yeah. Because it's 10, oopsie, 10 kilograms times 9.8, which equals 98. Okay, perfect. So we now have our two forces, right? And we know that this force is applied at 5 meters. So what is the torque or moment that is caused by that?
so it would be the moment equals the force 147 times the distance 5.
Yep. Which is?
735.
Yep. Perfect. And is that going to be positive or negative?
It'd be negative, right? Because weight is, oh, no, it'd be positive.
Yes. So it's going counterclockwise. So the weight is pushing it down this way, making the seesaw rotate like that, right? So yes, it would be negative, or sorry, positive, because it's counterclockwise. So we can say this one applies a counterclockwise moment. So we'll go ahead and start our moment z sum calculation down here. Okay. So moment z, the sum of equals 735, because that's what we just found, plus, and what are we going to add?
We're going to add the, wouldn't we add the other side?
Mm-hmm.
The moment for the other side?
Yes.
Which would be 98, sorry, it'd be equals the force times 98.
Well, 98
and
is
then,
our force.
Yeah, and then 98 times, hold on, blinking for a minute, 98, and then, can we solve this since we have two unknown variables?
We can solve it. We only have one unknown. So we have our weight here, right? And we're trying to find our distance here. So we can say 98 times distance is going to equal that torque, right? And then because we want this thing to not move, right? So it's saying net torque of 0. We can set this whole thing equal to 0, okay? Similar to how we do with our static equations for forces, right?
Right.
We almost always, in statics, we always set things to 0. So now what we can say is that this equation here, and we can just solve for d, and that's how we're going to get our distance. So, and actually, because 98 is downward, it's negative. So we should.
Yeah, I was going to say it should be negative.
Yeah.
Wouldn't it be 735 minus 98, or would it be 735
Yeah, I just
plus
put it
5?
in parentheses because if you add a negative, it becomes a negative. So yeah, now we can basically say 735 minus 98d equals 0, okay? And then what are we going to do to solve that?
Divide by d on both. Will we divide? No, add d on both sides.
So yeah, we'd add this term to both sides, right? So we'd
Okay.
have 735 equals 98d, and then what would we do after that?
Divide 98 on both sides.
Yep. So kind of running out of space here a little bit, but we divide by 98 on both sides. And that leaves us with, let's find out what that is. That leaves us with 7.5
0.5.
equals d. And now we know that if we want this seesaw to not move, then we need to put the 10 kilogram box 7.5 meters away from the pivot. Okay?
Okay.
So a way that kind of would translate in robotics is like, say you've got your robot and you have a big long arm, right? And your pivot, you know, is going to be your front wheel if it falls over, right? So this arm is real heavy, and you know that this is your pivot here, and you need to say, okay, how much weight do I need to put in the back of my robot if I don't want it to fall over? And that's basically the same exact problem as what we just did. Okay.
That would have been useful year before last.
Yes, it would have been useful a few years.
Yes.
Our very first year when we had Lucian B. Maxwell, he had a big problem with falling over. We actually had to put a ton of weight. We used tungsten carbide weights to try to get him to not fall over. But yeah, so that's why that's one way it's useful. There are other ways that you could use it if you want to do like a counterbalance sort of thing. You can. That's a great way to sort of apply this. Sort of like in this seesaw example. Basically, you have some sort of beam. You have some sort of pivot, right? And maybe you have a weight over here that you don't want falling, so you need to put a weight over here to counterbalance it, right? Which seems like something that's really simple and like weird, or simple and maybe not so useful, but there's a lot of uses for those simple sorts of things. So the second part of this asks what would happen if the moment arm of the second box was 8 meters. And the answer to that is, I don't want to do it out all the way, but you see how our moment arm here is 7.5?
Mm-hmm.
So what it's asking is, what if that was 8, right? So what if the 10 kilogram box was just out a little bit further? Can you tell me what would generally happen if that was the case?
It would it would cause the 10 kilogram box to lower the scale, lower the seesaw.
So yeah, it would cause the seesaw to start rotating that way because it's just pushing a little harder than this one is. Okay. So yeah, if it had an 8 meter moment arm, then it would just start to rotate to the right or clockwise, however you'd like to say. So okay, does this make sense? If you have any questions, definitely ask them.
It makes much more sense. Now I'm actually able to talk through it.
So we'll go ahead and go to the next one. These all kind of get progressively more difficult as we go. So if I go too fast or anything, just tell me to slow down. Okay, so this is very, very similar to the last problem, just a little bit more. So basically it's saying there are forces that are being applied, right? We can see here's a force, there's a force, there's a force, there's a force. And it's just wants us to calculate the net torque. So this one, it's not necessarily saying that it's going to equal up to 0. It's saying that this thing might be moving. Okay. And it just wants us to find out what the net torque is. So how do we do that? Basically, it's the same thing that we were going to do. It's going to be the sum of moments z equals all of our moments, right? So can you start me off with what some of our moments are going to be? So basically we have each of these, by the way, has, each of these has force and distance.
Okay, hold on, I'm just trying to finish up writing this out.
Yeah, totally.
So we need to, so should we start on the left side rather than the right side?
Yeah. The left side is going to be positive numbers because they'll cause, well, this, so if it's pointing down, it's going to cause a counterclockwise. As it's pointing up, it's going to cause a clockwise, right? So usually you want to put your positives first and then put your negatives after that, but it doesn't really matter which you do first, as long as you do them all.
Okay, so we would go 15 times 20.
And is that positive or negative?
Positive.
Is it?
Wait, hold on. No, it's negative, sorry.
Okay, so negative 15 times 20, then what?
Then you'd go negative 5 times 15.
Yep.
Sorry, negative 5 times 15. Then you'd go plus 5 times 5.
Yep.
Then you'd go plus 10 times 17.
Perfect. So, and then if we just do that all out, let's see, we got 170 plus.
Is it good if I just put it in parentheses just to, make it easier?
Put what in parentheses?
Like the negative 15 times 20 parentheses.
Oh, yeah. So let's see, 15 times 20, 300. So we got a negative 300. And we have a minus, I don't know why I did that out on there. 75. And then plus. So that is what our moment is going to be. So now we just need to add them all together, and that'll give us our net moment. So basically, we'll start with our positives, at least I prefer to. So 170 plus 25 minus 75 minus 300. And that gives us that our sum of moments in the z-axis is equal to negative 180 Newton meters. Okay? So can you tell me what that would mean in terms of how the seesaw is going to move?
So the rotation would be, could you repeat the question, please?
So how if the total moment is 100 or is negative 180 Newton meters, how is the seesaw going to move?
It'll move clockwise. Well, it'll move to the right, won't it?
Mm-hmm. So it'll move clockwise because it's negative, and 180 Newton meters is an okay amount, so it'll probably tilt pretty quick. But the important bit is, yes, it's going to be moving clockwise. So the next part of this question is we need to determine the force and distance from the axis of rotation, which that just means the pivot point, that would result in a net moment of 0. Okay? So we know that from all of these forces that are already given to us, we know that our net moment is a negative 180, right?
Mm-hmm.
So basically, it's just asking us to make that 0. So we just need to counteract that 180. So
Plus
If we
180.
add, yeah, if we add 180 Newton meters, then that'll fix it. How do we add 180 Newton meters though? Where do we need to put a force, and how big does that force need to be?
I'm not understanding what you mean by that.
So basically we need to add a force like these ones that is going to cause a 180 Newton meter torque. And this is a tricky question because there are multiple correct answers. So we could say, we know it's rotating counterclockwise, so we want it to be rotating. We need it to be positive, right? So we've got to, the force either has to be pushing up over here or pushing down over here, right? To try to counteract this. So one way we could do it is we could say, okay, well, 18 times 10 equals 180, right? So we could say 18 is our distance and 10 is our force, which equals 180 torque, okay? Because all we're trying to get is this 180 torque. So if we did that, then we could say, okay, we'll put over here, we'll put a force that is 10 newtons and the distance will equal 18 meters, okay? However, another perfectly acceptable thing to do would be to put a force here instead at distance equals 9 meters, but make the force bigger, right? And say 20 newtons. Because if we did that, we could still say 20 times 9 equals 180, right? And all we need is that 180. So,
Okay.
So another way to think about this would be, imagine that your dad's sitting on the left-hand side of the teeter-totter and you're sitting on the right-hand side of the teeter-totter. You think the teeter-totter is going to go down on your dad's side, right? Because he weighs more, assuming you're at equal distances. But if you wanted to balance it out, you might grab your little brother or your little sister and sit them on your side at some distance to balance those forces out to make it equal and level, right?
So basically, this problem is just asking, if you don't want the teeter-totter or the seesaw to move, where do you need to put how much weight? Which in FTC, because of that sort of arm problem or weight problem, tends to be pretty useful, because there's a lot of things that cause your robot to either tip or something on your robot to tip that you don't want to fall over. So being able to do this is a sort of surefire way of calculating that instead of just guessing. So, you know, in the notebook section, how there's a calculations like section of the notebook. Those most FTC teams don't have anything in there. But if you said, look, we had our robot, right, and we needed to go grab this little climber man who was over here, but this arm was just too heavy and our robot kept falling over and it was the worst. So we did some calculations and we found the net moment and we worked it all out, and we figured out that we needed to put 10 kilograms of weight in the back to fix that. You can put that in your calculation section. It shows that you had a problem, you figured out how to solve that problem, and you used actual engineering math to do so. And that's kind of what this is for. Especially if there's like, say, you know, in robots how they sometimes get cluttered. So like if you were looking down at your robot and like, you know, here are your wheels, you got to fit so many things. You got to fit your battery in there. You got to fit your phone in there. You probably have to fit a gyroscope in there. You've obviously going to have some motors. You know, your robot gets all cluttered. And so maybe you don't have a lot of places that you can put this weight. So your distance from your pivot point, which is going to probably be your front wheel, might have to be something. Like you might not be able to change your distance, in which case you can calculate the amount of weight that you need to put in that area to fix it. So that's kind of the application. Do you have any questions on this problem here?
No, I originally had a question about why we put a positive 10 newtons, but then I figured out because it's trying to counteract the balance of
Yes.
negative 15 and negative 5.
Yes. So another way to look at it, you know how we talked about our coordinate systems? Basically, if we were to put this whole seesaw on a coordinate system, right? Which it is, it's in a 2D coordinate system. So if we were to say, here's our coordinate system, here's y, here's x, everything this way is positive. So positive x, everything this way is negative x, everything up is positive y, and everything down is negative y, right? So if we have a distance that is out this way, it's going to be positive. If we have a distance out this way, it's going to be negative. If we have a force that's pointing down, it's going to be negative. And if we have a force that's pointing up, it's going to be positive, right? And if you just put those in, assuming those things, it'll sort itself out. So like if we look at this one, we can see 10 was pointing up, so it's positive. 17 is to the right, so it's positive. And then we could also say the same for things over here, like 15 is negative because it was to the left, but 20 is positive because it's going up, right? And that's kind of how all these work. 5 and the 5 and 5, really we should have written -5 times -5, which equals a positive number. But it's because it's a downward pointing force and it's a leftward distance. Okay? One of the best things for any sort of statics or physics is your coordinate system. Your coordinate system will save you, and if you mess it up, it will mess you up. Coordinates, that's why in almost every lecture I've taught, we have said coordinates are your friend. Okay, so I think, is this the last one or is there a 6? There is a 6. We might just do 5 because, well, let me look at 5.
I really didn't know how 6 played into what we learned because it had to do with tension. So
I think let's do 6 because 5 is more of the same. So 6 will be a little bit different because 1, it's got an angle, and 2, it's got a tension force. So I mentioned this last class period. Since you weren't here, you probably didn't get it, but tension force is just a different kind of force, same as any kind of, it's just like if you have something hanging from like a wire or a string or anything like that. So similarly to like if we have a box on a table, right, it's got its weight pushing down, but then the table is pushing up on it. That's because the table's pushing on it, right? If we in the opposite sense, have a box that is hanging from a wire, right? It still has its weight pulling down, but now it's got this wire pulling on it, right? So it's not a normal force, but there is a force there, and so we just label it as tension. Okay.
okay.
And the one thing about tension, so you know how normal force always is perpendicular to the surface?
Right.
So tension, the way tension works is always going to be acting in the direction of the cable. So like for this one, if we look at this point here, right? So we'll just say, here's our point. We have our bar and we have our cable. The tension force will be pointing the same direction as the cable. And the bar will be also applying a force on it, but it's not a tension force because it's not pulling. So tension forces are just another kind of force, and they always act in the direction of the thing that they are, which is a wire or a cable or something like that. Okay? So basically the same we were doing with other forces. So approaching this problem, basically what we're going to try to do is we're going to do our equations of equilibrium, right? So can you tell me if we're looking at this point right here, and we'll call this point A, right? I'll draw, this is point A over here. We're just looking at it by itself. What forces are going to be acting on A?
Weight.
Mm-hmm.
Wouldn't there also be tension?
Yep. And which direction would it be going?
To the angle to the left.
Yep. So since it tells us, we can see that it's 30 degrees, right? So we will say 30, and we will say it's a tension force. And then there's one more force.
So you said how earlier there wouldn't be a normal force, right?
So the tension would not cause a normal force is kind of weird because normal and applied force are basically the same thing. They're just looked at different. So the tension does not cause a normal force, but this bar here is pushing on A, right? So yeah, go ahead.
So it would be normal force then.
Yeah, so we can either call it normal or applied. It does not matter to me. Because it's not like a surface, we would probably call it an applied force, but it is technically a normal force is the thing. So either one is fine. Because we're going to be using F for the sum, I'm just going to call it in. So normal. Okay, perfect. So this is our free body diagram. We got that done. So now what we're looking for is, we know it's a 50 kilogram box. It's hung from a 5 meter long, 200 kilogram horizontal pole. So it's actually saying that this pole also has some weight, which is going to be important because that means we're gonna have two weights. One will be centered here. And the wire is attached to make sure that it does not rotate, okay? For the sake of simplicity, I'm gonna actually go ahead and say, don't worry about this weight. We're gonna just take that out. So we're gonna pretend like the pole has no mass, okay?
In reality, not possible.
Right, like usually it would have a mass, but just to make this a little bit simpler, we're gonna just take out that mass, okay? Okay, so we know that distance here is going to equals 5 meters, and we know it's a 50 kilogram box. So can you tell me what the weight force is gonna equal?
So you said it's a 50 kilogram box. So the weight would be, hold on. 49.
50 times 9.8.
Oh,
It's
sorry.
gonna be bigger than that, yeah. You're close though, kind of.
490. Sorry, I looked at the dimension rather than the weight.
Perfect. So 490 newtons. Cool. So we know our weight. That means that we can find some other things. We can find our part of our tension force, then we can find our tension force, then we can find our normal force. So let's go ahead and do those things. So basically, you remember how we split any force that's at an angle, we split into its x and y components? Do you remember that? Cool. So we're going to split our tension force into its x and y components because it's at an angle. So we have our Tx and we have our Ty, all right? And if we do our sum, right, our sum of forces, we'll say sum of forces in the y direction equals, and what am I going to put here?
Ty minus 490.
Yep. And what does that mean Ty is?
I mean, they're positive tension forces in the y direction. Is that what you're meaning?
Yes. It's a positive tension force in the y direction. So, but if Ty minus 490 equals 0, what is Ty?
Oh, 490.
Yep. So pretty easy. We now have our Ty. So we could so yeah, it wants us to find the full tension in the wire, so that's what we're going to do. But basically, when we're doing the moments of this, We don't actually need to worry about the normal or the TX because they're applied so that they would pass through the pivot point. Since we're trying to find the tension in the wire, I mean, there's a few ways we could do it. One of them can include these. I don't think I really want to do that. I'd like to keep it a little simpler. So let's go ahead and just find out what the tension in the wire is. We have our Ty. What is one way that we could find T? We also have our angle.
Could we just use a trigonometric function?
Yes, we could.
I don't know. So I'm gonna rewrite this triangle.
So yeah, which trig function should we use?
Yeah, absolutely. So we want sine opposite of hypotenuse.
Yep. So sine 30, which is our angle, is going to equal our opposite, which is Ty, over our hypotenuse, which is T, right? So if we do that,
yeah, 490.
Yeah, if we do that, then basically we can multiply both sides by T and then divide both sides by sine 30. So this is going to end up being T equals Ty divided by sine 30. Okay? And
so
what does that equal?
T 980.
Yep, so sine 30 is always going to equal 0.5, okay?
Yeah,
so
I remember that. I just
Yeah. So 980 equals T. So we have found our tension force. We did not end up needing to use this 5 meters here because I took out the weight of the rod. If the weight of the rod were there, then we would have had to do a little bit more. And what we basically would have had to do is say halfway through the rod is where the force is going to be applied because it's the center of mass, right? So you can always take all of the force of, or all of the weight, or all of the mass of something and just apply it to a single point at the center of mass if you're looking at that point, basically. So we could have said that whole force is being applied at the center of mass. We know that it's a 5 meter rod, so we can say that half of that is 2.5. And then we would have done some other things basically to find the tension in the wire, which would be either we could have gone a moment route or we could have gone a similar forces route. And that's going to be the case with a lot of statics problems, is that there are multiple ways to solve them. Sometimes you have just a lot more equations than you do unknowns, which is great. It's a great problem to have. So do you have any questions on this?
not really.
Okay. So I do want to just show you one more thing, which is question 5, and I'll just kind of tell you the answers to the, we'll go over all the answers so that when people look over this, they can see them. But something that's interesting about question 5 is that basically it's saying it's got a 18 kilogram object on it and tells you the distance from the left leg it is. So from here to here is 0.8. And it's saying the mass of the tabletop itself is 6 kilograms. And then it's asking you what's the force. Well, it's asking the force exerted on each leg. And the reason that that specifically is interesting is we can't just look at the forces. Because if we just looked at the forces, we'd basically say, okay, 18 times 9.8 plus 6 times 9.8, because that's the mass, and then both of them multiplied by gravity, is going to equal our weight force, right? And then we'd say normal equals weight, and we'd say, okay, well, there's these two normal forces applied here, and they're each half of the weight, right? But that's wrong. And the reason it's wrong is because the weight is not applied evenly. If the box was right in the middle of the table, the normal force on both legs would be the same. But because it's not, the force on this leg is going to be more than the force on this leg, right? So this one will be a very little force, and this one will be a larger force. And we don't need to do this out right now, but the reason that that is interesting is, in robotics specifically, is if you have a robot with 4 wheels, right? And let's say they're Mecanum wheels, right? So you need all of your wheels to be able to rotate well for you to get the movement that you want. Like if you rotate all your wheels inward, you may go off to a side, right? Because you're strafing. That's how Mecanums work. The problem is if I put a ton of weight over here and no weight over here, this
You're gonna
wheel,
like spin out of control.
yeah, this wheel is going to make a ton of contact with the ground, and this wheel is almost not going to be touching at all, right? So if you ever have problems, and a way we do it in robotics is we put a scale under each wheel to see just how much it's sort of supporting. But another way to do that is to calculate where you're putting your weights. You know, if you have your robot, you can say, well, I'm going to put a 0.2 kilogram battery here, or I'm going to put some weight of phone over here, or I'm going to put a grabber mechanism that's this heavy over here. And you can actually calculate the force on all 4 of your wheels. So there's a guess and check way to do things, a trial way, and also a mathematical way. And if you do the mathematical way, you can put it in your calculations section, and the judges will probably be impressed that you took the time to do those calculations to show that you have near equal traction on all of your wheels, right? So I just wanted to show you that because it applies to the robots that you guys use. It also applies in general to things like even if you're using a table, maybe one of your legs can't hold up that much weight, and you don't want the leg to break. So it's just an interesting problem. If you have some time to go back and do problem 5, I think you'll be able to now. I'll let you know. Basically, you're going to have to use sum of forces in the y and sum of moments. Okay. So those are the 2 equations that you're going to need. They'll both equal 0. And then they'll equal the whatever forces and moments there are. But I would urge you to go and do this problem one on your own now that we've kind of gone over the others. So yeah, do you have any questions on any of this?
No, this makes much more sense. Thank you.
Perfect. So next class, and I'm kind of mentioning this because it's also the recap video. Next class, we're going to be doing full system dynamics or full system statics, which means we're going to be looking at whole things, not just parts of things. Oof, what do you want? Okay, so full system statics, we're going to be looking kind of at the same stuff we've been looking at, but we're now going to go into 3 dimensions, okay? So that's kind of the plan next class. Make sure you practice with moments and with forces so that we are prepared next class to really delve into that. And once we finish this, we're going to kind of flip switch and start going into motors and power, which is different than what we've been doing. So yeah, if you don't have any questions, then I think we're good to go. I'm going to go ahead and stop recording.